Hello everyone, welcome back to the lectures of Process Modeling and Simulation course. I am Mohammad Haris Humayun, lecturer, Department of Chemical Engineering, Commerce University, Islamabad, Lahore campus, and we are currently studying module number 1, Physical Properties and Thermodynamic Models. We have previously discussed the textbooks and reference books required for this course in our previous videos, and so far, we have covered the first three exercises in our previous videos that we have determined the basic physical properties for pure components. We have used a system property method, which is the same like the thermodynamic property package, and we have used ideal property method as well. So our today's activity is related to the estimation or the calculation of vapor pressure for pure components in Aspen Plus. So let's quickly go to this activity and see what is the simulation requirement and how we will simulate it. So this activity, which is our activity number 4, is related to CLO number 1 and CLO number 4. CLO number 1 is basically related to the fundamentals or basics of this course, and we will study how we have achieved this CLO. 4 is related to the analysis, and obviously this portion include the analysis as well. How? The case is to determine the vapor pressure with ideal property method, and this is the basic representation of vapor pressure. We already know the definition of vapor pressure, that it is the pressure of vapor exerted in equilibrium with a liquid or solid in a closed container. So we are assuming a liquid which is water present in a closed container, and we will calculate the vapor pressure at different temperatures. So our question number 1 is that what happens in the vapor pressure when the temperature is at 60 degrees centigrade. This is the water temperature at 60 degrees centigrade. Our question number 2 is that what happens in pressure when the temperature is 100 degrees centigrade. Our question number 3 is what happens with a half mass, means if we reduce the mass to half, what will be the effect on vapor pressure, means if we reduce from 1 kg to 0.5 kg or liters, then what will be the effect on vapor pressure. What happens with an other material, means if we replace water with some other material, then what will be the effect on vapor pressure, or what will be its vapor pressure. And what happens if inert gas such as nitrogen was filled originally, then what will be its effect on वेपर प्रेशर. सो बेसिकली आप लोगों ने वाटर के केस में ये तीन क्वेश्चन नंबर 1 2 3, इस केस में आप दूसरा मटेरियल को ही लेंगे और अगेन इस केस में आप वाटर और नाइट्रोजन को इकट्ठे लेके चलेंगे और देखेंगे कि वेपर प्रेशर पे क्या इम्पैक्ट पड़ता है, क्या नाइट्रोजन के होने से वाटर के वेपर प्रेशर पे कोई फर्क पड़ता है या नहीं पड़ता है. तो ये चीज हमने इसमें बेसिकली देखनी है. दिस इज द सेम स्टेटमेंट. Objective of today's simulation is that we can have clear idea of vapor pressure, and by giving specifications in simulation we can result pure component analysis. As I have told you that this activity is related to CLO number 4, so analysis part is covered in this activity. In problem description, in a closed tank water is contained without any air in vapor phase. Find difference in each temperature and mass change. Our first task is to specify the components, and we will specify water and acetone. We can also specify nitrogen at this stage as well, and we will specify it because nitrogen is also involved. So water for our first three questions and question number 5 as well, and acetone for question number 4 and nitrogen for question number 5. And then we will select the ideal property method as we have discussed before. Then we will go to the pure analysis. In pure analysis, we will select the property package as ideal, and in thermodynamic, we will scroll it down and we will select vapor pressure as you can see here. And then we will select our component water from here, and then we will select list of values from here because we are not given a range. We are given two values, that one is 60 degrees centigrade and number 2 is 100 degrees centigrade. And after that we will run analysis, and after analysis we will get the values of vapor pressure at different temperatures at 60 degrees centigrade and at 100 degrees centigrade. Then we will select acetone and we'll do the same calculation, and we will again get the values of vapor pressure at two different temperatures for acetone. Then we will compare for ideal property package and then for Peng-Robinson, that which of the property package is best suited in this condition. We will come at this point later. We will select water and nitrogen simultaneously, and then we will check its. The results will be discussed at the later stage, but first we will do the simulation. So basically आप लोगों ने करना क्या है कि आप लोगों ने सबसे पहले तो कंपोनेंट सिलेक्ट कर लिया, वाटर, एसीटोन और नाइट्रोजन को। फिर आप लोगों ने आइडियल प्रॉपर्टी पैकेज को सिलेक्ट कर लिया। फिर आपने वेपर प्रेशर को सिलेक्ट कर लिया, क्योंकि आपको पता है पिछली एक्टिविटी में भी हमने वेपर प्रेशर को ही पीटी डायग्राम डेवलप की थी, तो वेपर प्रेशर को सिलेक्ट किया था। लेकिन उस टाइम हमने डिफरेंट लिस्ट ऑफ वैल्यूज, यानी हमने अपर बाउंड और लोअर बाउंड दोनों वैल्यूज दी थी और इंटरवल दिया था। लेकिन इस केस में ऐसा नहीं है। इस केस में आपको सिर्फ 60 डिग्री सेंटीग्रेड और 100 डिग्री सेंटीग्रेड की वैल्यूज गिवन है, तो आपने उन्हीं वैल्यूज को वाटर के लिए यूज करना है। जब आप 60 और 100 को यूज कर लेंगे तो आपको ये क्वेश्चन 1 का आंसर भी आ जाएगा और क्वेश्चन 2 का भी आंसर आ जाएगा। फिर जब आप एसीटोन के लिए करेंगे तो आपको क्वेश्चन 4 का आंसर आ जाएगा, और जब आप नाइट्रोजन को मिक्स करके करेंगे, जो कि ये वाला केस है, तो आपको क्वेश्चन 5 का आंसर भी आ जाएगा। क्वेश्चन 3 का आंसर हम सबसे एंड में डिस्कस करेंगे, क्योंकि इसी में ही उसका आंसर है, जो कि ये लिखा हुआ है, लेकिन इसको हम इन द एंड डिस्कस करेंगे। सो लेट्स गो टू द एस्पन प्लस, एंड फर्स्ट वी विल सेलेक्ट वाटर, acetone and nitrogen, and click next, and we will select ideal property package and then click run, and after running it, check the results, that results are available, and after that go to pure analysis, and the property package which is selected is ideal. In property type it's the thermodynamic property, and we had selected that it's PL, vapor pressure. We have discussed in our previous activity where we have developed the PT diagram. And now we will select our component water, because in our first two problems, that what happens in the vapor pressure of water at 60 degree centigrade and at 100 degree centigrade. So we will select water, and then in the temperature range, we had not been given any starting point and not the end point and not the intervals, but we are given the list of values, that what will happen at 60 degree centigrade and what will happen at 100 degree centigrade. So once after giving these values, you see this run button has been active and this run analysis has been active. So you can either click on run or on this run to get your values. For example, if I click this run, then results are present over here. If you go to results, then you can see that at temperature 60 degrees centigrade, the vapor pressure of water is zero point 0.2 bar approximately, and at 100 degrees centigrade it's 1.013 bar. We had already discussed in our PT diagram that ideal method satisfies it. Ideal property package can be used for water as well to determine the vapor pressure, that at 100 degrees centigrade the vapor pressure is 1.013 bar, which we have studied in our literature as well. Now our first two questions are answered. What we will do, we will deselect this, unselect this. What we will do, we will click on water and we click this button, component to be included in the property calculation, and we will take it back, and now we will use acetone. And after selecting acetone with the same conditions of 60 and 100 degree centigrade, run analysis, and in results you can see that at 60 degree centigrade the vapor pressure is 1.15. You see, the pressure is high than 1.013 bar. It means that the boiling point of acetone is less than 60 degree centigrade. इस बात को समझने की बहुत ज्यादा जरूरत है कि वाटर के केस में आपका बॉइलिंग पॉइंट होता है 100 डिग्री सेंटीग्रेड, और वो होता है 1.013 बार पे, जो कि आपने देखा भी पिछली एक्सरसाइज में, और अभी इस एक्सरसाइज में भी आप लोगों ने देखा। लेकिन अगर आप एसीटोन की बात करें तो 60 डिग्री सेंटीग्रेड पे उसका जो वेपर प्रेशर है 1.1543 है। इसका मतलब है कि जो एसीटोन है वो इससे पहले ही बॉयल आउट हो चुकी हुई है। उसका जो बॉइलिंग पॉइंट है बेसिकली वो 56 डिग्री सेंटीग्रेड होता है, एंड सिमिलरली 100 पे जो है वो 3.73 बार है। सिमिलरली अब आप एसीटोन को डीसिलेक्ट कर लें, डीसिलेक्टिंग द एसीटोन and selecting water and nitrogen, and when you have selected water and nitrogen, again you click run and go to results to see that whether there is a change in the vapor pressure of water with the addition of nitrogen or not. There is no change of vapor pressure of water. When you have selected only water, when you had included the nitrogen, the vapor pressure values are same. It means that with the change in mass or with the change in moles of water or a liquid, the vapor pressure doesn't change. So this also satisfied our question number 3. If I take you back to the problem statement was that what happens with a half mass in case you have included water and nitrogen, and assuming that there is half weightage of water and half weightage of nitrogen, you see there is no change in the vapor pressure of water. So it means that vapor pressure is independent of mass or mole, and that's we have already discussed in our literature. So we have studied this, that what happens in pressure at 60 degrees centigrade, at 100 degrees centigrade, what happens with an other material which was acetone, what happens with a half mass answered with question number 5, where we had included the nitrogen here. So that's how you can extract or calculate the property value of vapor pressure. In our question number 5, at nitrogen as component, and vapor pressure is a pure component property and is independent of mass, moles, or presence of any other component. So our last task is to compare results which we obtain from ideal method and from Peng-Robinson method. I will go back to Aspen Plus, and in property method, in methods, I will select Peng-Robinson from here, and I will again run it, and after running it, results are obviously available, and in selected methods, you see both methods have been selected. So now scroll it down, go to analysis, pure input, and in case of ideal, select it as Peng-Robinson equation of state, remove nitrogen from here, and now run it. You see in results that 100 degree centigrade temperature, the pressure is 0.945, which violates the real time principle, because the vapor pressure of water at 100 degrees centigrade should be 1.013 bar, but it's 0.945. It means that Peg Robinson is not suitable for liquids. It cannot be used for liquids. It can be used for gases or vapors. Let me re-explain it कि देखें जैसे 100 डिग्री सेंटीग्रेड है, तो हम कहते हैं जी पानी बॉयल होगा 100 डिग्री सेंटीग्रेड, तो उसके करस्पॉन्डिंग हम प्रेशर कहते हैं जी 1.013 बार, तो उसका बेसिकली वो वेपर प्रेशर होता है। लेकिन जब आप पेंग्रो बेंसन को सिलेक्ट कर रहे हैं तो आप देखें कि वो कितना प्रेशर बता रहा है 0.945, तो ये तो गलत प्रेशर है, और अगर आप इसी को लेके आगे कैलकुलेशंस करेंगे तो वो भी गलत होंगी, वो फेक होंगी कैलकुलेशंस, वो करेक्ट इनएक्यूरेट कैलकुलेशन होगी। तो जैसा हमने अपने पहले लेक्चर में डिस्कस किया था इस कोर्स के, कि अगर आप सिमुलेशन का सॉल्यूशन सही देंगे तो ही आपके रिजल्ट्स में एक्यूरेसी आएगी। अगर आपकी बैकग्राउंड खराब है या आपने बैकग्राउंड में गलत प्रॉपर्टी पैकेज सिलेक्ट किया तो आपका रिजल्ट्स कभी भी एक्यूरेट नहीं होंगे। तो आप देख लीजिए कि पेग्रोमेंसन देने से आपके रिजल्ट्स एक्यूरेट कभी भी नहीं आ सकते फॉर वाटर केस, जब वो लिक्विड फॉर्म में है। अगर वाटर वेपर फॉर्म में चला जाता है तो फिर रिजल्ट्स कुछ और होंगे। सिमिलरली फॉर एसीटोन, इफ यू क्लिक इट बैक and select acetone and again run it, you can either click on this run analysis as well. Then you see at 100 degrees centigrade, the vapor pressure is 3.66485. Let me take you to the slides that for ideal, this value was 1.013 bar, but for Peng-Robinson, this value is 0.945. So it means that Peng-Robinson cannot be used for water. However, for acetone, this value for ideal system was 3.72919, while for Peng-Robinson, in case of Peng-Robinson, it's 3.66485, while acetone is already a vapor at this stage. So it means, and if you go back to literature, this value is correct, while this value is not correct. So it means that Peng-Robinson property package can be used for vapors. In case of water, since it was liquid, so it cannot be used. But in case of acetone, Peng-Robinson can be used. So that's how you compute the values of vapor pressure in Aspen Plus. In the next lecture, we will discuss the non-ideal behavior of gases using equation of states. Thank you.